This is a talk about executors for C++. It's not how to use them. It's what they can do for you and how hard it actually is to get executors right. And it's called a long story, and that long story hasn't ended yet. So we don't have a final executor interface yet in C++. So what's the mission of an executor? Well, some of you may know the async problem. So if you look at the code, and sorry, the setup here is not very optimal, who of you believes that this will put out hello world? Okay. Who of you think it will put out world hello? Who of you think it will put out just garbage or just some mix of those letters? And who of you think it's just undefined? Okay, there were actually very few of the right answer, because the right answer is it will guaranteed put out hello world. And that is not really known to a lot of people. You have absolutely no concurrency here. And the reason for that, and that is a little bit aside, is the async problem. And the async actually returns a future. And normally destructors of the futures don't block, except if the future comes from an async. So in our code here, well, we don't actually capture the return value. So you get a future out of the async, and, well, you don't capture that future, so the destructor of that future is immediately called. And that destructor blocks for the ending of the task, and so you get absolutely no concurrency here. And that is actually good, because lifetime control is very important for C++. This is what makes C++ different from all those managed languages like C# or Java or anything else. And the problem with the async is you have absolutely no control about the execution agent that actually runs your task. And so you have no idea how long it actually runs. And if that task actually references some of objects that are also used otherwise, well, you really need to know when it actually finishes to use those objects. And this is why we have the blocking. The blocking is actually good. The problem is that we have, for a future, different behavior in the destructor, whether it comes from an async or from somewhere else. And the reason for that is, well, you simply have nothing to control when the lifetime of your async or of your task ends. So that is why the original async is not really optimal. Another motivation, pipelines. We actually had a proposal for that, and well, the example here comes from an old UPSLA workshop, how to present concurrency to students. And so the exercise is actually, okay, you have a restaurant and you have a number of orders coming in, and then you have some chefs who prepare the meals, and then you have some waiters who actually deliver those meals, and if there is nothing to do anymore, everything ends. And this can easily be written using that pipeline proposal. So you say you have 3 chefs and 4 waiters, and the orders come in, and the orders come in through some communication mechanism to the chefs, and the meals prepared by the chefs come through some communication mechanisms to the waiters, and then eventually it ends. And this can be run on a thread pool or on something else. So what actually are the requirements for the executors? Well, to run tasks and to give some control about lifetime. Well, so we got a very simple proposal originally. That came from Google. There was somehow a similar proposal from Microsoft, and eventually they just joined the proposals. And so the original executor interface, well, it was an abstract base class, and it had one function just to put a new task to the executor, and the executor eventually executes that task. And as usual, if you give some requirements to programmers, they will give you more than you actually ask for. Maybe not exactly what you asked for, but they will give you something else. So you also got the uninitiated task count. That turns out to be pretty useful sometimes. So that was nice. That is not really the original interface, but that is what it boiled down to. And then we had the default executor and some mechanism to set the default executor. Well, that sounds nice. And then the proposal also proposed some concrete executors, not only the interface, but also some real executors that actually do some work. Of course, a thread pool. Then a serial executor. This just runs one task after the other on the same thread, but on a different thread than the caller. The inline executor, well, that actually calls the function right away on your calling thread. And the loop executor is something in between, but it's also serial. And then you have the thread executor that just spawns off a new task, a new thread for each task you give it. And those are actually interesting, because they have completely different semantics concurrency-wise. The thread executor, which just spawns a new thread for each task, well, that is really concurrent. The serial executor isn't really concurrent, because it does one task after the other. Nowadays, we call that it has parallel execution semantics, and that is a little bit counterintuitive. Parallel means it can actually be serial, while concurrent means it has to be in parallel. This is how it is. The point is parallel runs on as many cores as you have, and if you have only one core, you don't get any parallelism. So with that proposal, we can actually solve the async problem. So you can either define a new launch policy, say launch executor, and will run on the default executor. Well, maybe that's not such a great idea, because it sometimes really makes a difference, because you have the set default executor. you have no idea what guarantees you actually get from the executor. Is it a concurrent one or just a parallel one? And well, but anyway, you could use that one. And even the normal standard async could use the default executor. But it still have to block on the future destructor because this is what people expect now. And as I said, sometimes it's very important that you know when the lifetime of your task has finished, so you can just clean up all the global objects it might use. And the most important interface would be the last one. You just give it the specific executor you want to run the task on. So that's nice. If you look at the pipelines, well, this can really be implemented on the proposal as well. So, nice. Problems are solved. We have executors, and that is why the concurrency study group decided to put this proposal into the concurrency TS. Well, we have used 15 minutes of the hour, so you know it's not the end of the story. Because now the real discussion started. Well, some of that already started before. And one of the problems is, well, the original proposal just used an abstract base class interface. That actually is very useful. It's not a template concept, it's an abstract base class. It's not part of the type, which is not really important for function, but for structures that can be very important. So we did that mistake. I think it was a mistake with the containers, that the allocator is actually part of the type. And so we got scoped allocators in C++11 to work around that. And so that is one point. The executor, if it's an abstract base class, is not part of the type. And the second thing is it can cross binary interfaces. So you can actually provide a library that takes an executor. And that library can be binary only, and it gets the executor, it gets the abstract base class, it knows what function it can call on that, so everything is fine. However, sometimes it simply costs too much. If you have a lot of very small tasks, you don't want the overhead not only of one virtual function call, but actually of two, because what your add function actually takes is a stat function, and that internally uses a virtual function call as well. So you actually have two virtual function calls for each task that you start on that executor, and yeah, sometimes that costs a lot. And we got more requirements. So one of them is .then. So we have .then, the .then proposal, so the future .then, which is a continuation that runs after that future is ready. So if your first task has finished, you know what you want to run after that. And so you just start an async with something, and this time you actually capture you use that future that you get from the async, and then you say, okay, on this future you want to put a continuation, and that continuation should run on my specific executor. Okay, that's fine. That works with the old proposal. The problem is, if you don't give it an executor, on which thread should it preferably run? Well, in a lot of cases, it would be very useful if the continuation runs on the same thread as the original function, the original task. However, how does the .zen know that? If you don't control the whole library, but only your very small thing, then you might have a problem to know that. So you have no mechanism right now to transfer that information with the previous proposal. Another thing is, well, I live in the embedded world. Well, I'm just curious, how many of you do embedded systems? Okay, thanks, interesting. That would definitely be different in Switzerland, for example, because in Switzerland, nearly all C++ is on embedded systems. And, but on embedded systems, well, sometimes I just have to use real-time and real-time priorities. So we have something like the pipeline. In this case, it's just the data concentrator, and it has two producers who read from data from two different devices, and then we have a consumer that takes all the data, does some calculations on those, and finally reacts on that one or stores it somewhere or whatever. The main point here is you have two producers that read from external devices, and one of those devices doesn't really have an internal buffer, so that really needs a very high priority so that you don't miss any data. If it signals you, okay, data is available, you really have to go for that data independent of all the other things that your core is currently doing. So you need a very high priority on that one. You don't really need high priority on the other ones. So you want to run that concentrator, well, and one of the tasks has a different priority than the others. Well, how do you communicate that? Next example, ASIO. Who of you has already used Boost ASIO? Oh, good. So you know what I'm talking about. So this is about asynchronous input-output. Well, input-output is asynchronous by default, by definition, essentially. And so this is really meant to be a high-performance input-output library. And so it generally wants to run the continuations of your I/O on the same thread where the operating system returns from your I/O call. And often you want to run concurrently, but sometimes you actually want to run cooperatively on one single thread. So all your tasks don't have to synchronize anything. And this is actually doable with ASIO. And it definitely doesn't want the overhead of the futures, because futures have to synchronize, and if you know you run on a single thread anyway, well, you don't want the overhead of the futures. And it wants, well, it provides its own executor, but it should also be able to run on user-defined executors, which has additional knowledge about the system and maybe additional functionality. So system-specific asynchronous events like signals, interrupts, mailboxes that you have on small embedded devices, and things like that. And well, this ASIO library is actually pretty old by now, and so there's a lot of experience with that one. But of course, that is very specific requirements for asynchronous input-output. So now we have new requirements. So we got new proposals. So there is an O missing here. And so the first proposal was actually by Chris Koloff, based on ASIO. So ASIO has internally executors, so he proposed just that. And it has several interesting things. One of them is it makes a difference between the executor that you use as your interface and the execution context that actually holds all your state. The threads, if you have a thread pool, you have your threads, you have the queue with all the tasks to be run and so on. That is a state. That is a very heavyweight thing. You typically don't want to copy that one. You might want to move it, but even that might be pretty heavy. But definitely not copyable. And the executor, that is only a very, very lightweight interface and handle to that one. And but that is what you use as interface. And he proposed several concrete executors, the system executor, which just starts a new thread for each task, the strand, which is like the serial executor, a thread pool, of course, and the loop executor. I have to admit I don't remember what this one exactly is. Probably like the loop executor from the other proposal. And it had a number of customization points. And that's interesting. So one of the customization points were the continuation tokens. So you could actually use that to run the continuation of some I/O directly on the thread which did your I/O. So the continuation could be used as a synchronization mechanism. And yeah, I think a better name for that would actually be synchronization token. Because it can also be used to define the concurrency mechanism that you use. So he actually has also a continuation token that uses cooperative multitasking and just uses yield to wait for something right now, to block for something. And that yield then returns to your executor, and then it can run something else. The second customization point is he actually didn't have a single add function, but actually 3 functions: dispatch, post, and defer. And if you look back to the original proposal, they had an inline executor and a serial and all the other executors. So the interesting thing of the inline executors was that it runs the function, the task, right away. So it actually blocks for finishing that function. And some people said, well, this might be very surprising to some of the people who use executors. So that might not be a good idea. So they actually dropped the inline executor and said, OK, the add function is never allowed to block. However, sometimes it's actually useful to have such an inline executor. So what Chris Koloff actually has proposes is to have the dispatch function, which actually can do that. It can run the function right away. So it can actually block your caller until the task is done. It doesn't have to, but it can do that. So that's, from the behavior, definitely a different interface than the post function, which is the nearest one to the add function. So post is just, OK, here's a new task, run it, don't block for it right now, and run it somewhere. And then he has a third function, the defer function, which just says, well, that task that I give to you here is actually some kind of continuation of what I'm currently doing. So it might be useful to run that task maybe on the same thread that I'm currently running, just when I wait for something or something else. So it's more a hint. It's not really a different behavior. It's just a hint to the executor, but it's a very useful hint to get high-performance execution. And the third customization point is the associated executor thing. So I told you the executor in this proposal is just a very lightweight thing. And the real thing underneath is the execution context. So you can actually define your own executor on top of an existing execution context. So you don't have to implement your own thread pool just because you want to give some additional information or to use some additional information. So for example, I implemented my real-time executor just on top, well, in my case, just a thread executor. So I just spawned a new thread for each thing because then the operating system priorities actually kick in. And so that lightweight executor on top of that, that actually contains the additional information whether something is a high priority task or a low priority task. So if we come back to my proposal here, what you actually see is I have a different object here. And this is an object that has just a different priority. So I have two different executors here. Those are just lightweight handles on the same execution context. And one has normal priority and one has a pretty high priority. So this interface with the associated executor, this in general allows for providing any info from the application point to the executor. Without my data concentrator needs to know anything about that one. So that was Chris Kolov's proposal. But we also got another proposal from Google. Chris Mason was at this time, and he actually started to work on the original Google proposal, but just did, well, a lot of work on that one. And tried to fit into the new requirements and address the abstract base class thing. So what he actually proposes is an executor just as a concept. So it's essentially template-based. So templates can just take an executor as template argument, and then you can use that interface. So our add function, which was renamed to spawn, is not a virtual function anymore. But it's again a template over the actual function type. So you don't have to use that function, so you don't get the overhead of that function here as well. So we definitely addressed this one. And the other thing that he also added was exactly something like the associated executor. So he proposed a task wrapper, and originally he made a mistake there, but after some discussion, now he actually does it the right way. So that is fine. But that's the only customization point he proposes. And then we got a third proposal by NVIDIA, essentially, because they were implementing the parallel algorithm TS. And in that, well, originally in that proposal for the parallel algorithms were also an executor interface. So you give an executor, and your algorithm will just run on that executor. And, well, we did get out the parallel algorithms as a TS, but not the executors anywhere. So that was stripped off from the current TS, but we still want to have it at some time. So they looked into what do they actually need from an executor to implement the parallel algorithms on top of an executor interface. And they decided not to come up with just another one, another executor interface, but they said, well, what we actually propose is a traits class. And this just adapts to whatever executor you have. And that traits class first gives you the semantics of the actual executor. So I talked before about the concurrent executors, which is always more or less in parallel, and the parallel executor, which might be serial, and then we also have weakly parallel, where you are not allowed to do any synchronization at all, at least no blocking synchronization. And well, if you implement something, you typically want to know what semantics you actually get. So they wanted to know this in the traits. Then they wanted to know the future type that you actually get for the return when a task returns. Well, that is something none of the other proposals actually covered, because they don't talk about futures at all. Well, the ASIO proposal talks about that in some kind. So one of those continuation tokens actually produces a future. But generally they say, well, it's not the job of the executor to deal with your results and to deal with any exceptions or things like that. That is something else that has to deal with that. But the parallel algorithms people, they said, well, we need some kind of future, and they want to know what type that actually is. They said, okay, it doesn't have to be std future, it can be some other future type, but they need to know what type that is. Okay, fine. And of course, they want to know how they have to start a new task. And that task has to return exactly this future type. And they also want to start a lot of tasks at the same time. So they say, okay, well, that is NVIDIA. So they don't have 1 core or 4 cores, they have several hundred cores. So they want to spawn off several hundred tasks. And if you write an executor, it might be much more efficient just to create 100 tasks at the same time than one after the other. So they came up with an additional interface. Okay, we want to start so many tasks. The interesting thing about the executor traits is, well, the traits actually allow for wrapping your executor. And you can add all the functionality that this specific trait requires inside of the trait. You don't have to do it in the executor. So for example, the future thing, well, as I said, the normal proposals don't really talk about futures. Well, you can add that. If your underlying executor doesn't provide such a bulk interface, well, you just can write in your traits class your for loop and start all those tasks. So I think that's a very useful approach, but of course, this is again only one aspect, one specific domain for the parallel algorithm. So what's the status quo? What do we have right now? Well, the original Google proposal with several modifications was accepted by the concurrency study group into the concurrency TS February last year in Issaquah, just a few miles from here. Well, that was in February. In June last year, people came, well, Chris Koloff until then never came to a meeting. He just wrote proposals, but he didn't come to the meetings. And he was in Rapperswil, but Dietmar Kühl actually presented that to the concurrency group. And after that discussion, well, nearly everybody said, okay, we have to remove the original proposal from the concurrency TS. We are not there yet. We cannot use that one as a TS. And, but also, and this means strongly in favor, neutral, against, or strongly against. So only 2 people were weakly against removing the original proposal from the TS, but no strong opposition on that one. On the other hand, most people were not really happy with the ASIO proposal as it stands. So they said, well, we need more work on that one. So when we finally asked the question, okay, should we use now the ASIO proposal as the new executor model in our TS, well, the group was pretty much split. So definitely no consensus on that one. So SG1 decided to have an additional meeting between the Rapperswil meeting and the Urbana-Champaign meeting in October or November last year. So they met 2014 over in Redmond. And there Chris Mason came with his new version of the Google proposal. And well, there were a lot of Microsoft people there. There were a lot of Google people there at that meeting, and they were all in favor of that proposal. So when they asked the question, okay, should we actually restart with this proposal? Yeah, most people were in favor of that, and those 2 who were strongly against were not even in Redmond. They were on the phone. And one of them was me, and one of them was somebody from the UK. Because we said, well, yeah, that's not really what we need. And the NVIDIA proposal that was discussed in May in Lenexa, but we didn't take a vote. We thought, well, okay, it's a very interesting approach, but we are not ready to vote on that one yet. So that's the status quo. So what do we really need? And maybe it's actually useful to look a little bit at the bigger picture. So the original C++ standard standardized the standard template library, and part of that standard template library were the allocators. But essentially nobody actually used ever that allocator directly. That was used by the containers. So the allocators is a very low-level building block, and you put the interesting thing that's actually used by your programs, by your applications. Well, that is in some middle layer. And for the executors, that middle layer might be an ASIO proposal. Well, just async to start a new task. Well, to run a task on that executor and get a future back and do fiddling with all the future things like exceptions and things like that. The pipeline proposal that we have seen, the flow graph as it was in TBB, or still is in TBB, the parallel algorithms, something like an event loop that's very important in embedded systems, but also in other systems. So the executor actually isn't something that is used by applications directly, but it's something that is used by the middle layer, by some additional components that actually, some of them might be standardized, some of them might not, but they will use the executor interface. And there's a general rule: if you have more info, then you can do a better job. Well, what kind of information might be useful for the implementation of an executor? Well, for example, what's the relationship of the task that you run to your caller? That might be useful. Or is the task that you actually are giving to the executor something that's long running, or something that is very short running, just compute that function and then you're done? Or is it something like a server which will live more or less forever? Is a function, is a task actually contains it internal blocking calls, or doesn't it? Is it actually a task that should be run again and again and again, which is often done in embedded systems? Do you have some specific priority, as we have already seen? And how do you want to get the information back of your task? Maybe you are not interested in that information at all. If you are running a server, for example, well, if you're spawning off a server, you're not interested in any return value. You don't expect it to give you any return value. Well, all that information is very specific to some executors, to some domains. And probably nothing of that should be directly in the interface of the executor. But there should be a mechanism for me as application programmer to give this information to my underlying executor that I controlled as well. If I start a pipeline on an executor, I possibly created that executor. So I know what executor I have as an application programmer. But I don't control the actual call to the executor. So I need some mechanism to give this information from the application to the underlying executor. And, well, this is exactly what the associated executor can do if you have that very lightweight handle, because then you can just use that mechanism to transfer that information. Well, and yeah, there's still a little bit more. And I'm actually pretty happy that core is sitting there. Pretty happy. And well, coroutines are very important for some types of asynchronicity. And ASIO, for example, works pretty well together with coroutines. But I believe, I might be wrong, but I believe that the current proposal that we have with the async resume approach doesn't really work together with executors. Maybe we can do that. Do you know? Okay, good to know. I will definitely have to look at. Oh, okay. So Gore actually, when he's the main proposer of the async resume proposal, he just told me that you can probably do exactly that by saying async and give that an executor. And I have to admit, I really have to look at that part of the proposal. And we really need that composability. So the status quo is we don't have an executor interface. So what do we need to do? Well, executors are a very, very important building block for anything that is even remotely concurrent, asynchronous, parallel. But they should be very low level. They should provide you the interface for the immediate layer. They should not provide you an interface for the application program. But what that interface will be, well, we still have no agreement on that one. And, well, we have some very specific experience. So we have a lot of experience from ASIO. We have experience now a little bit from the parallel algorithm people. We also have the experience of all the Google people and what they have done inside Google. But I still believe that's not the whole story. And we probably need a lot more use cases to see what we actually need. So, yeah, one question is, what is a task? So, what information do you need to give to an executor if you give some higher level mechanism a task to run? Is it really just a function? Or is it a function plus some information? And if it is plus some information, well, what information is it? And how do you get that? So what we really need to look into, okay, what interface do we need between the executor and the middle layer? But in a way that the higher layer, the application, actually can transport all the information it wishes to the underlying executor. And as I said, we definitely shouldn't standardize everything. But we should standardize something that is open enough so that other people can build on that and do their own things outside of the standard. So, yeah, I was actually one of those people who said, well, I really want to go forward with the ASIO proposal, not with the Chris Mason proposal. On the other hand, I think the ASIO proposal actually is very, very complex. And I actually have implemented my own executors on top of the ASIO proposal, and yeah, it just has some things that I think you shouldn't need to do. But the ASIO proposal actually provides me those 3 customization points that I think are very useful. Well, there might be more customization points that might be useful, but I simply don't know them yet. And Chris Mason's proposal only provides one of those customization points, the associated executor. So it actually has that interface to transport some information from the application layer down to the executor through the middle layer. But it doesn't have anything like continuation tokens, and it doesn't have the three-function interface. And personally, I don't really like the three-function interface. I'm not completely sure that we only have those three hints we want to give from the middle layer down to the executors. So yeah, we definitely need to do more work. Coroutines, well, Gore just told me that they are more cooperative than I thought, which is very, very good. Thank you. And, well, that's it. Any questions? Well,
I'll just stay seated. So in using the executor that we have in the code that I work on, one of the issues that comes up is you have a large number of tasks that need to be run, and those tasks consume resources, and you would really like the executor to be aware of the resource consumption so that it could choose tasks to perhaps pause or abandon or what have you. And there are other things as well, but I'll just leave the question at that. And I just wondered whether you'd given consideration to that kind of thing.
Well, I think everybody has heard the question, so I don't have to repeat it. Well, yeah, this is something that especially the ASIO proposal has put a lot of thought into that one. And the point is that is a very interesting thing, because part of that is between my middle layer and the executor, and part of that is between the application and the executor. So it's actually two different things. And if I look back at those three customization points, I have to admit I don't think that's really covered. But it's definitely good input. Thank you. Any other questions?
Yeah, it's related to, but not necessarily just about the executor. Have you guys talked about the cancellations for the tasks in general and something that the executor could look at when the task was canceled before it's run?
So you actually say you put a task on an executor, and then you decide, well, you don't need it anymore, so you cancel it, and the executor shouldn't run it. No. We haven't thought about this use case, and I think none of the proposals has any remove function. So which says, okay, remove that task from your queue if it's not already started. And that again doesn't fit very well into my middle layer and application layer thing, because sometimes it's a middle layer that notices, okay, I don't need that anymore. And that could actually do something, because that has a direct interface to the executor. The application, but sometimes it's actually the application layer that says, well, okay, I started here something, using whatever new task, but I don't need that anymore. But it doesn't actually have a direct interface to the executor. So,
but it could. You know, like what if the future would have an interface like that?
Well, an executor definitely could have an interface like that. I don't remember that it ever came up in the discussion, but well, that's definitely interesting input as well. Thanks.
I just want to second that. I did a similar thing where we used a token. We called it a token that we passed to the tasks so that they know if they need to keep doing work. And sometimes tasks would take longer to run than maybe our framework expected. And so we would kick off another task to help it. These things could be on cores, they could be distributed. We didn't build the framework to know if it was on the machine or distributed, but these tasks would be sent out. And if tasks weren't coming back as fast as we wanted, then we would kick off more. But there was plenty of opportunity for the token to tell the task, hey, it's been handled now. Stop your work, or don't even kick. We created 10 more, but you don't need to send that out. There was cost in sending out. Just a comment.
Yeah. Okay, but after that, I actually think it might be doable just using that lightweight executor thing, associated executor, because there you can add whatever information you want, and you can just put in a Boolean, for example, okay, don't run it anymore, or yeah, you still need to run it, something like that. But that is only if it really comes from the application. If it comes from the medium layer, well, yeah.
One more question. I think I missed the part at the beginning of your presentation when you talked about when async fires and it's launched async. And you said it's desirable to know that the task will finish by the time the extraction happens for that future.
Yeah.
I don't think it's desirable when the launch is async. I think it's desirable when it's deferred, but when it's async, why wouldn't I wait for the future explicitly? Why?
No, that's not the point. The point here is your task runs. It references some objects while it runs. You must make sure that those objects are still available when the task accesses them. And that is why you need control over when that task actually finishes.
Sure, wouldn't I then wait on my main thread on that future, and then I know that, hey, it completed, I can delete those?
Exactly. That is why we actually give you the future from the async, because then you can wait on that future, and everything is fine. The problem is if you don't wait, if you don't take that future and don't wait for it, then you have a problem.
Are there usages for that? Like, who would do that?
Well, that is exactly the point. When we originally designed future and async, we thought, no, there is no use for that. But it turned out that a lot of people actually use it exactly that way. They have fire and forget tasks. Yeah. So they are not interested in the future. They just want to start their task. And the point is we actually have two different use cases, but only one interface for them. And that is a problem.
I think we have time for one last quick question.
Okay, so in your slide about your real-time priorities and your non-real-time, you gave the priority to the executor handle and not to the task that you fired off. In my use case, we actually need something that knows that this task takes 1/5 of the memory that is available, and you can only run 5, but you've got 32 cores, so you need to sort of, knapsack the RAM, and it doesn't work that way.
Well, the point here was that executor handle is a very, very, very lightweight thing. So you can actually create a new executor for each single task. And this way, you can just put the information that you want to put to the task into that thing. So actually, it is a little bit a misnomer. So it wasn't apparent to me when I looked at the interface that I could use it that way. But after I actually worked with it, I found out, well, this is exactly the thing I need to put whatever information I want into the task and give it to the underlying execution context in this case. So you can actually use it that way. Okay. I think time is over. I'm still around for the rest of the conference. Thank you.